I'll show you in a sec, but basically what it does, so it has an API for like this kind of stuff. Like you say, okay, I want to set B1 pin to output, right? Whereas without this, you have to muck around with the internal state registers of the AVR. So you have to do some bit mask manipulation, whatever. But this is much nicer. So this is what Arduino does, and the other magic ingredient is this package, AVR program, because what this allows you is to mark certain static constants as being put not into main RAM, but into the flash. So they're not going to be copied over basically when you start your program, right? And that means that you save the space on that. So I can use the, and then I wrote some macros. This program input bytes is so that you can, let me show you.
Sorry, what is the memory model for that chip?
It's a Harvard architecture. So you have the, so your CPU, I mean, yeah, or like, okay, all of this is obviously on one chip, but then your CPU, and it has the main RAM, and it has flash.
So and so does not act, it doesn't act like a hard drive in a Unix system, I guess.
No, no. So the CPU, so you can only fetch from here. Like you can read and write, but you can't execute from this side.
Right. Is there, can you effectively mmap something in, like without the address translation?
So what? So you have completely, there's no address translation.
Yeah.
You have completely different opcodes for reading from here versus reading and writing here. Like it's not just a different address, the opcode itself is different.
Yeah.
So you have, but you have opcodes for reading from program. So this is called program in AVR. And you have a way of reading bytes from this individual. It is slower than reading from here, and it takes more energy. I mean, well, of course, energy doesn't matter of us, but like this is a microcontroller, all of these, right? It's for someone somewhere this matters. So you can read from here bytes, but the important thing is that you can only fetch from here. There's no opcode to like take in a byte and execute it, or take in a byte and pretend that is the next instruction.
Because the Harvard architecture has two different memory spaces.
Yeah, that's what Harvard architecture means. Yes, it's not von Neumann. Yeah. So and you know, you might ask about, okay, what about this direction? What about writing into program? That like for our purposes here, you can pretend that you can't do that. Because what happens in reality is that there are ways of doing that, but it's super clunky. Like it's not going to be byte based, but you might be able to like take like a 1K window that you can then overwrite completely. It's going to be very slow, right? But this is not really suited for storing data, runtime data there. So what this AVR program library does is it allows you to, in your program, say that, okay, I have this static, just like you can see like here, it's just static array of bytes, and you mark it as program, and that means that it's going to be part of the thing you upload into Flash, but it's not going to be fetched at the beginning and put into RAM. And you know, in our case, what we do, so I wrote this macro that instead of basically generating the data, it just allows you to read in a file at compile time and put that into an array of bytes. And so this one is, this file is 4 kilobytes. So
that must be a procedural macro, I guess, right?
Yes. Yeah, well, I mean, it reads from this kilobyte. So that means that like 1/8 of this thing is filled in from this file, right? So you would never be able to fit that here. So yeah, but we don't even try because it's in program, which means it's part here, but that's it. And then we need to have explicit instructions to read bytes from it. And of course, in our case, so for this particular board, the one on the photo, right? So of course, there's one more RAM, which is very far, like here, This is the serial RAM. And this is something that you can communicate with using the SPI interface. Right? And this is like orders of magnitude slower because it's SPI, I think it runs at like a couple hundred kilohertz or something like that. Right? And it's like a 1-bit channel. So you send in 8 bits to change something here. But it doesn't matter because the original computer was so slow, like, right? Like, all of this is going to be way faster than what you had on the original machine. And then, of course, we also use the SPI to draw on the screen. Because the screen, like, actually it's the other way around. So the screen uses SPI, and that's why I picked an SPI RAM as well. I didn't want to muck around with having both SPI and I2C.
To interface with the screen, did you also have to write your own library for that?
Yes, I get into that. I mean, but it's not a raw LCD. It has small controller on it, so it understands. It has its own protocol of SPI messages. Wait a second. So where was I going with this? Yeah. So all right. So you have this package which links to the engine, and like. This is much harder to debug because this you're gonna run on this, like a small box on your, like a small piece of plastic, right? So my advice would be if you do anything like this, always structure it like this, so that you can debug your engine or your backend or whatever your functionality separate from the AVR or like the embedded context, right? So because I was doing all the debugging of making sure that my chip-based implementation is correct using this thing. Okay, and so then we have the...
So why is that, if you have an emulator, can't you have an emulator where you also see which calls go in and out, which makes it much easier then, and then once you've got it running in there, hopefully the chip implements exactly the same.
But that's exactly what I'm saying. Like I wrote the chip-based implementation this separate package and then linked it with the SDL frontend, so I could run it or like of course so in the SDL version, like you can just like print in the middle of whatever, right? Like you can, it doesn't need to be a real time. Like this one is nice because it allows you to actually play it or like use it in real time, but it doesn't have to be that. You could have like even this one, right? If I change some flags, it would like print stuff here. Yeah, and of course you're gonna test. Like you can apply all the usual software engineering for this. And then, so let me just show you that it really does work. So you can build this, and so now in 2024, all of this just works. So you can use. I'm using here January nightly because that's when I last played around with this. AVR backend is not yet in the stable Rust. But if you use any recent daily, it just works now. So you can see this just builds with, January 1st, okay, nice. And then, you get something that you could upload straight away onto this thing. Now, unfortunately, I don't have this with me because, well, like I said, I only found out today that I'm gonna do this. And we moved recently, so it's not easy to find it like small, right? But anyway, but what I can show you is that, of course, there are simulators for AVR. Like, real people write real things for these microcontrollers, not like stupid toys like I do. So of course they have and this is, like, there's big company behind AVR. So it's like a real thing that there are tooling to debug your AVR programs. And this was very important back in 2017, because all the ways that the LVM backend failed, it was always just generating it was generating some AVR machine code, but not the one that would do the thing that I wrote in Rust. So to be able to see what is going on there, I depended very much on having good emulators. Now it's less of an issue because it really does seem to be working out. But it's still fun that, of course, what you can do is you can compile the AVR target, the Rust version that targets AVR, you can compile it with Rust, and then you can pass it to this thing, which is using the AVR emulator, or simulator, hooked up to some virtual implementation of the same SP protocol that is spoken by the real serial memory and the real LCD. So then what you see here is so this is now of course not running at real time. You can see it's kind of slow because the AVR simulator is super accurate because, it's like sub-cycle accurate, whatever, which we don't need of course, but because it's using an off-the-shelf industrial strength simulator, it's not that fast. But doesn't matter, it's still not that slow, right? Like it's still, you can see that it works. And so you can use this to, for example, attach GDB to it. This is super nice, but it's a very different thing. But you couldn't like print in the middle of your program because you will need to have some way of printing on the AVR, which of course is just a small plastic package on your breadboard, right? So what does it mean to print from there? So it's like two different worlds. And so, okay, so now just to answer your question about like what does it actually look like in the inside to interface with the peripherals. So the AVR chip itself has an SPI interface, so you don't have to big bang, you don't have to implement what it means to send something out by SPI. You can just, there's a special register, you set it to an 8-bit value, and it will shift it out. And so, like I said, there's this Arduino library which has this very nice interface to doing that. So you see that this is super readable compared to writing magic values to magic memory addresses. And then, yeah, if you want to send something out, you just send it out, basically. And to address either the screen or the memory, that goes by a separate wire. So for example, if I want to talk to the screen, then what I need to do is I need to set my pin. So of course, so this D3 is just because like that's the port. Like if you were to trace it on the schematics, you would see that one of these should go to this one actually. I think this one, right? Yeah. So this we can't see it there, but this one says port D3. D3 is connected to the chip select of the LCD. So you have to pull that low. That's how you tell this guy to start listening, and the RAM is not listening, even though they're connected to the same SPI line. And then you send out your data, right? Byte by byte. And then you have to look up the datasheet of the LCD to figure out how to talk to it. So the datasheet will tell you that, okay, you send these magic bytes, and then you set this other input to, like you pull it high, and that means that instead of listening for an instruction, it will now listen for data, and then you just send out in 8-bit, like basically 8-pixel stripes, you just send out your data. And it's the exact same story for the memory, which is, so like I said, it's also connected to SPI. So if you want to read from it, you pull low a different port, but this is the one now that instead of connected to this guy, it's connected to this guy. So this you pull low, and then you send out the magic number that again you need to look up in the datasheet, that you want to read, and then you send out the first, the high byte of the address, and then you send out the low byte because this is larger than 256 bytes, so you need more than 1 byte to address, and then you get back the result by the same SPI, and that's it. And you need to write. Difference is basically that the command instead of 3 is 2, and 2 means write, 3 means read. Exact same thing, and of course, if you send 2, then you need to send the value that you're writing, but it's the exact same story. So this is what it looks like to interface with the peripherals, and then the actual, and then there's some fun stuff with the timers. So on the chip 8, you have a way of waiting for 1/60th of a second. In your game, you can write or any number of 60th of a second. This was trivial to implement on the original hardware because it was just connected to the video interrupt, which the screen runs at 60 FPS. But of course, in this thing, there's no such thing, so you have to implement it yourself. So the AVR has timers, and then you can see again using the Arduino library, this is infinitely nicer than it used to be. Instead of mucking around with magic values, you can use nice enums and set it to prescaler of 64, and then you divide your frequency by 64. That will give, if you were counting up this much, you get a timer every second, but if you divide it by 60 more, and this is of course a compile time calculation, because it's a constant. This is super nice because you couldn't, like, these chips don't have division instructions, right? But this doesn't matter because this is all happening at compile time. And that's basically it. So I guess the other interesting thing, but I kind of went over that already, is that the emulator itself is written in idiomatic Rust. So you have, like an ADP, and then you have this decoder, and then you match on the decoder. And you can, if you look at the machine code that is generated, you can see that the Rust compiler and LLVM, and it's mostly, I think, Rust. Of course, it does the thing that you would hope it does, which is to recognize the case-of-case structure. So it will not, like the code it generates is the mashup of these two, right? So instead of switching on this number and then generate into memory some value that represents this opcode, and then looking at that and switching on that, it's put together. So this function and this function combine into something that just looks at the one 4-bit value and then switches into this, which is exactly what you would want. So it's super efficient code that it generates. So you get all the niceties of Rust on a very, very tiny platform that I think at scale it costs like less than $1, and you can run it for. But I mean, okay, you couldn't run this for years on a battery because it communicates with the LCD, of course, all the time, because it's a real-time game that you're running. But the chip itself, like if you were using some sleeping mode in it, so I'm just saying it's a completely different world from a normal computer, and it's much better. And yeah, it works from Rust. I guess that's all I wanted to. So yeah.
You said earlier that the no STD and the match didn't work.
No, not because of no STD. Like nothing worked. Like match was one of the high-level constructs that didn't work because it was just complex enough to not work. So what I mean by that is that the AVR backend just barely worked. The LLVM AVR backend just barely worked to have literally the simplest possible program. Just thinking an LED for that to work. I mean.
So it would be compiler error because like match translation was not
If you were lucky, then yes. That was very infrequent. So usually what happened was that you would get some AVR machine code, but it would not do the right thing. So either that or you get some internal crash from LLVM, but usually it was just generating some bogus machine code. And then you have to learn enough AVR machine code that you can read what comes out and that you can look in the emulator, I mean the AVR simulator, not your emulator, but the AVR simulator to see what happens when you try to run that and figure out where it goes wrong, and then learn enough about LLVM to figure out how to fix it, blah, blah. So like I said, I have a blog post about this from back in the day. It was a long journey, but it doesn't matter now because it all works now. So now you can, I can say that you can just use Rust for AVR development or for the tiny microcontroller development. And I can recommend it because for two reasons. One is that it's a lot of fun because it's such a different world. Everything is tiny, you have full control over the machine. Like there's no OS, right? And the other thing is that things that would fit for Rust. Like I wouldn't see any reason to use Rust like on the desktop, right? Because like you have all the exactly. Like you don't need to worry about like you can have a garbage collection, right? Like that's not a big price to pay on a computer, and then you don't have to get bogged down with low-level languages, and so yeah. But for these, so like Rust is super nice fit for these very constrained systems.
So how would this be different from, let's say I want to program, I don't know much about electronics, but an ESP32 or something?
It's the same story. Well, I mean, okay. High level is exactly the same. And then low level, a lot of it comes down to how good is the ESP32 support of LLVM. I believe there is an LLVM backend now. I don't know how well it works because, like I said, this was supposed to work and then it didn't. And I had the exact same story. By the way, a couple of years later, I did the exact same story again for the 6502 backend of LLVM. And so I got the same, yeah, I should probably mention that. Okay, yeah. So I ended up taking the exact same chip 8 Rust interpreter and writing a front end for it in Commodore 64. So you can also run the same stuff on, moving ahead. So now this is early 80s technology instead of late 70s. And this is like a real home computer that a lot of people, of course, knew. And it still has COD status. And it had the same story that it doesn't, like, it kind of worked, but there were lots of rough edges. In this one, it was less about correctness and more about performance. Like in my blog, I have lots of stuff about wait, where is that? There's somewhere I have some stuff about the quality of the code it generates. It's just very, very bad. Everything is very slow, but it works kind of. And this one I haven't updated. So this is 2021. Unlike the AVR stuff, I haven't gone back yet. I should at some point, but.
So the code quality is at like the LLVM stage where?
No, by code quality I mean the quality of the machine code that they generate.
Exactly. So it's not the Rust engineering.
No, not really. So
it's an LLVM issue.
Yes, but the separation is not that clear cut in my experience. So, for example, for matches, right? Like for anything that is compiled ultimately into LLVM into a jump table, for example, like you would think that you can just generate whatever and then it's LLVM's problem to make it work. But it turned out that we had to play some games around making sure that these tables will end up being in program. Because as far as LLVM is concerned, by default, it's just data, so it's going to be put not just into program, but into operating memory, and then that uses up a lot of memory. If you only have 2K of RAM, then it matters. So there is some interplay between the Rust side and the LLVM side usually that makes things a bit more complicated. But in this case, yeah, so I would say that for 6502 backend, it really is just that the backend is not as good as it could be, and also so AVR is much more, even though it's a tiny resource-constrained thing, but it's much more modern than the 6502, and there's lots of things that the 6502 itself struggles with if you try to compile a modern language to it. It doesn't really have a native stack. The things that are usually fast in modern CPUs are exactly the kind of things that you don't want to do in a 6502 because those are slow, and so on and so forth. So, yeah. But it works. So it was kind of thing where I think my takeaway was that, oh yeah, I think this is yeah, so generated code like this, and it's like, so all this is doing is like, this should be 4 lines of machine code that just in a loop clears out a big area of memory. And you might think, oh, but maybe it's more efficient because it's like unrolled, but it's not really. Like it does completely stupid things in the middle of it. Yeah.
What is that instruction set called?
So this is 6502.
Okay.
This is the 6502 version, not the AVR. The AVR stuff, like I never had performance problems with it. It was always correctness problems with it, which is not to say that the performance is perfect. It's more like it was always good enough that I never needed to look into it. Whereas this one was so bad that I needed to at least look into it to see if there's anything I could improve. But I was like, oh, this is like I need to come back to this in a couple of years. which is now. So I should go back because I think enough time has passed that it's worth a second look. Yeah.
How does the code for the actual game look?
So yeah, sure. Very good question. Okay, let's see. I have somewhere. I have one that I wrote just in the process of learning about the GPA, right? So a lot of these unfortunately don't come with source. But it's not really source because it's a machine. So the whole point of the GPA was that you get very good mileage out of a small number of instructions. So the programs tend to be quite short, like a couple hundred bytes can get you something that does that is a recognizably fun game. So this is so all of these are up to, let's say, the last 10 years. All the GPA games would be written basically in GPA assembly. So you can see that, okay, so you have function calls and you have a bunch of, where is my cursor? I can see that right. So you have like a bunch of registers. You have 16 registers, and then you have some stupid mnemonics, and then I really don't know what to say about this, to be honest. So there's only 20-something instructions, you have 16 registers, you have 4K of RAM, and that's it. And then you can see that most of it is just comments because I knew that I would never be able to figure out what it does ever again. So this is not the game that I showed you, because the one I showed you is a good game that someone competent wrote. This is a 2048 game. Maybe I can show you that. It should work in theory. So, this is the, it doesn't even have animation, but you can kind of make it out. So instead of having powers of 2, it only shows you the power because of our notifications. So like, this is a 1, and this is a 2, and this is a 4. So if I move everything to the left, so now I can move these 2 zeros into 1, right? And if I move this down, well, that wasn't a good move, I guess. What did I do? Up. And then, and then if I go down now, right? Bring it down and then right. Yeah, and then down again. So yeah, you can see that, okay, this is much nicer with animation, but yeah, that's why I'm not using my own game to demonstrate the GPA, because it's not well done, but you can do nicer things. Like, of course, there are games that have proper animation and stuff. And then in the last 10 years or so, people have written like higher level assemblers, you could say, or like fancy macro assemblers and some fancy higher level constructs. So these days, instead of just writing directly GPA instructions, you would just use those, and then you would have random variables that are mapped to memory and stuff. I don't know.
Do these like GPA instructions then have like awareness of the peripherals? Like, how does
Yes. So this is super overfit for making games for these machines originally. So you have a machine, like a GPA machine instruction. There is one specifically for taking an 8 by n sprite, where n is a parameter, and putting it on the screen at a given location. That is a single instruction. And this is the draw instruction. So I think it's called draw. Let me see. Should be something here. But of course, when I say sprite, I don't mean this one, like this guy. So this means that take the sprite, the current sprite, and draw it at V2, V3. So V2, V3 are 2 registers, those are the X and Y coordinate. Take a 5 pixel tall sprite, pointed to by the special address register, because you can't fit an address to a general purpose register because the addresses are 12 bits and the registers are 8 bits. So you have to do some magic first. But once you have the right address in your address register for the sprite data, then with a single instruction, so this is 2 bytes in the chip 8 unit, right? 2 bytes will get you a sprite at a given location at a given height. But when I say sprite, it's not like a modern, it's not like on the C64 where a sprite would be on top of the graphics and you can move it around, right? Like these days, a sprite usually means that you can draw something on the screen, and if you move it, then the background will come back from behind it, right? So they're like float on top of the screen. No, this is not that. This is just statically like stamping the thing on the screen. There's no such concept as background, there's no such concept as moving a sprite. If you want to move a sprite, you need to draw the same sprite at the same place, because drawing has XOR semantics, and then you can draw it at the new location. That's how you move something. This is a product of its time, right? But yeah, so you have the instructions to draw, but you have only one instruction. This is the instruction to draw on the screen. You have one instruction to wait, which basically sends the special timer register to a number, and that number is decremented at 60 Hertz. And then you have another instruction that tells you if the number is 0 or not. So if you want to wait, the only option is to set this number and then busy wait. That's how. Or wait for a draw, because also when you draw, it will wait for the end of the frame. So you can't draw 2 sprites inside a single frame. On the original machine, I mean. These days it's trivial to leave these restrictions, but a lot of games depend on these restrictions for timing purposes. So this is the kind and the same for the keyboard input. So you have an instruction that basically reads in, waits for a key to be pressed and then reads in the 4-bit value of that key into a register. Or you have another one which, given a specific 4-bit index, like a specific key, you can branch on whether it's pressed or not. So you have both key down, key up, and you have key press.
So can you wrap it up in 2 minutes? Yeah.
Sorry?
Can you wrap it up in 2 minutes?
Sorry?
Can you wrap it up in 2 minutes?
Oh yeah, I mean, I'm basically done. Right? We're just having free form discussion. It's basically the end of it. And then my next project that I started, but then kind of got 90% done and then never finished, I hope to get back there one day, was using the same setup for the Erdi boy, which is another AVR based. It's like the big boy version of what I built. So this is amateur hour that I just put together breadboard, whereas this is the real deal. This is an AVR microcontroller. It has a nice OLED display, it has 4 directional buttons and so on, but it is ultimately the same, underneath is the same microcontroller, so you should be able to use Rust for it. So I started writing a Rust game, writing a game in Rust for the Erdi boy, and yeah, it's 90% done, but I also Steam, I don't know.
So just not the question, when you wait for the key to press,
yeah,
is it busy loop or wait block?
So like I said, you have both. So you have an instruction that says wait for the next key press, and once it's done, write the index of that key into this register. So that one will wait. That one is a single thing. But then you have another instruction which says, is key 3 pressed? Then if yes, then jump, otherwise continue. By the way, another fun fact, all the jump instructions are always one instruction jump ahead. So it's not, you can't put an address, it's not, in any sane machine code, right? You have jump into address X, and then address X is here, and then you have programs here, inserted here, and this will jump here, right? Or even better example, instead of jump, it could be jump if non-zero, right? Not on the chip 8. On the chip 8, the only thing you can do is you can say jump if not 0. It's not just, it's skip if not 0. And what that means is that the next instruction, the single next instruction is skipped over if the condition holds. So you have this kind of jump, but only unconditionally. All the conditions. So if you want to do this, you have to put the jump here. Just a small remark, just to get a good feel of how exotic the chip is. So I should at some point make sure that I finish this game because it's. Oh, that's actually okay. That's like for next time because we're running out of time. But I just quickly mentioned that when I was doing this is what it looks like. This has sound as well because the Erdi boy has a buzzer connected. So this is a port. This is a demake of an OC64 game called Wizard of War.
Yeah, but it looks like you have some box looking, dinosaur looking thing.
So the problem is that I can't die, as you can see.
Yeah,
actually, I think that's just no, that's not true. That's just because I think I commented something out for testing purposes. I have that implemented. I just don't have some of the bosses implemented yet. But it's supposed to just work. Do we have sound on this? Yes, it has sound. Yeah, but not sound effects, just the sound when the game starts. So for this one, but this is for another day. What I found amazing is that once I got this working well enough, both in SDL and on the actual AVR hardware, I wanted to show it to people. So how do you show it to people? No one's gonna not that many people have Erdi boys, and even those that do, it's like kind of a hassle to download, plug it into your computer and stuff. No one is going to download a random program to run on their computer. So you want to run it in the browser, right? And so what I found is that it's actually super easy with Rust and the WebAssembly backend of LLVM to take a program that is already written in this style of splitting into the platform agnostic parts that implement the game logic and the front end part that implements, like in this case, SDL to draw the screen. And you can see that this is much higher resolution, by the way, because it's different. Like Erdi boy just happens to have a nicer screen than the old phone screen I use, right? So I have the. Let me just the side. And then we like down. Okay. I'm not sure if I still turn. Okay. I just want to show you the WebAssembly version running in the browser because that was amazing. It was like half an hour of work from scratch. That was the opposite of the AVR and the 65 experience. It really does work out of the box. From knowing nothing about it to getting it into an actual web browser took me like half an hour. Everything worked first try, and the JavaScript thing I had to write around it was like 20 lines of code, or maybe not even. So can recommend. Okay. I think it's gonna be there.
With this drawing running.
Sorry?
With this drawing running.
On this, this is the latest, the latest LTS Ubuntu, like 4.04.
That was Mate.
It is Mate on top of Ubuntu, but the distribution is Ubuntu. The desktop is Mate, and then everything else is 25 years of accumulated craft. You know how that is. So okay. So you can see that this works in the browser. This is really. And this probably I can die. Oh no, it's still the thing. Okay. Okay, you have to take my word for this, but I really did have dying working at some point. But anyway, I'm not saying it's finished anyway, right? It doesn't matter. So I think the teleporters at least work. No. Oh, this is some shitty version. Okay, there's more stuff. So yeah, so this was super nice experience getting this onto the browser. That is, yeah. I think the portals were closed. Now they work. Yeah. So if it's like this, then it's closed. It opens and closes at some time intervals to make it more exciting. Yeah. So now I can teleport.
So did you have to write the interface? So I guess that's painting on a canvas in the browser? Or?
Yes, it is running on a canvas. So the way I don't have time, right? I don't have time for
Yeah.
Next time. Yeah. So that's basically it, and then some.
Okay, thank you.